Sanja is an assistant professor at the University of Toronto, a faculty member at the Vector Institute, an AI chair at CFAR, and she is the director of AI at Nvidia. Prior to that array of appointments, she was a research assistant professor at TTI in Chicago, and even earlier she did a postdoc with Sven Dickinson at U of T. Sanja has been publishing highly impactful work. Now associate, Costa says. Wow, great. Sanja has been publishing highly impactful work in language understanding and computer vision, particularly in areas where those two topics meet. Selections of Sanja's work have been highly publicized in Canada to the extent that I'm pretty sure everyone in Toronto knows about algorithms that generate pop songs and generate fashion suggestions, and that's Sanja's work. With her team at Nvidia, Sanja has also been developing models that generate objects and composite them into scenes, and even generate full 3D scene simulations, going all the way from latent vector to scene graph to pixels. In all, it's a very inspiring body of work, and we're glad to have you with us, Sanja.
Yeah, thanks, Adam, for the nice introduction. And yeah, I got tenure in July. All right, so yeah, I joined Nvidia a little bit over 2 years ago. That was May 2018. And when I started, I was thinking about how can I contribute, what can I do, and Nvidia is at the heart is a graphics company, so 3D was really something compelling to work on. And today I'm going to tell you a little bit what we have done in the past 2 years, mainly around 3D content creation. All right, so 3D content is basically everywhere, from architecture where you need to create buildings and interior layouts, to gaming. Almost all modern games have really nice 3D content. Movies where directors basically want these characters, even humans, but animals, to do things that they actually can do. So you need to do computer graphics. VR, which is particularly compelling right now that everyone is at home, right? You want to basically generate your friend in your room or a tiger in your room or whatever. And then there is, healthcare and robotics. And this is particularly the domains where I'm interested in. And what I mean by 3D content for this domain is mainly around simulation. So before you can deploy a robot to the real world, you basically need to test it or even to train it in like a simulated virtual environment. All right, so you need to put a car in a virtual city and then test it against all sorts of difficult scenarios. And only when you're sure that it's going to perform well, you can actually go into the real world. And it's actually really hard to create these simulators. And a lot of my work has been around how can we automate some of this process. All right, so here I'm just gonna show you a video. Hopefully it's not too loud. Here, which is Nvidia's Drive Sim Simulator. I think this video is maybe now 2 years old, so a bit outdated. It's a lot better these days. Where essentially, people have built this here highway, but now they also have bigger virtual environments where you simulate other cars. You can randomize weather, you can randomize where other cars are going to be, you can randomize all the different traffic signs, scenarios. Yeah?
The video is a little loud. You have to hear your voice. Is there a way you can...
Yeah, here. Okay, is better?
Yes.
Great. Importantly, in the simulation, because it's just a graphics engine, ground truth comes for free. Right, so you can just render links, you can render roads, cars, all the segmentation, which is impossible, very hard to label by hand. It's all for free. Plus, there's some ground truth you can render that you can never get in the real world, like materials and optical flow and things like that. Right, so simulation is actually really good, and graphics can help here. Right, so kind of my dream when I started thinking about this was, can we help all those engineers that are basically creating all these things by hand? So they need to create virtual cities, they need to create all the assets that are going to go into this, maybe some manual handcrafting of behavior trees, is kind of driving these cars and pedestrians around. So how can we help to automate this? Right. So my dream would be, can you just download some 3D model of some city, let's say New York or Toronto, whatever, and make it come to life? So place all the different cars around in interesting scenarios and make them drive around. And then you can put an ego car in here and be tested against all these different scenarios. This is just to show you how complicated this actually is. So we ask an Nvidia artist to try to recreate the kitty scene in the top with the available assets. So
Manual content creation pipelines require significant human effort. Here, we see a person creating a scene aligned with a given real-world image. The artist places scene elements, edits their poses, textures, as well as scene or global properties, such as weather, lighting, camera position. This process ended up taking 4 hours for this particular scene.
Yeah, 4 hours for this just one scene. So this is very slow, right? You can imagine how hard it is to actually build this at scale.
Manual content creation pipelines
So probably all of you are familiar with the GTA game, the Grand Theft Auto. And in that game, basically they brought Los Angeles to life. And it took 1,000 people, 1,000 artists and engineers working on this for over 3 years. And basically they were going around the city, taking some footage and then trying to recreate that world in a game engine, right? So my goal would be, can we just go around, take footage of the city and convert this into 3D scenes. Right now I'm showing static scenes, but ultimately this should also be videos. So we should be able to simulate these cars. So as little supervision as possible, just footage. And you should be able to train your own simulators given the location of the world that you're in. All right, so what am I kind of thinking around what's useful AI for 3D content creation, at least for simulation? We need to be able to create some tools for creating scene layouts, right? So these worlds, assets as well, so objects, 3D objects you're gonna put in the scene, and then dynamics, right? So scenarios, behavior, and even animation. And I think all these tools ultimately need to be interactive because you cannot automate everything perfectly. So the human and artist should be in the loop, but you should make their job as easy as possible. All right, so we have a couple of different threads on this that are ultimately hopefully going to come together. And I'm going to talk a little bit about this work. So I'm going to start with how can we actually synthesize world. So in games in particular, like different scenes are being created with procedural models or probabilistic grammars, where, for example, if I wanted to synthesize a street scenes, I would sample some number of lanes on the road, and then on each lane I would sample some number of cars, and then next to lane is a sidewalk, and again a sidewalk can have a number of people and trees next to it. So there are some rules that define how actually a scene looks like. Okay. And there's a bunch of things here that the artists need to write in order to create valid scenes. One thing is just, some distribution, so some structured distribution. So how many cars typically should I be sampling? And then as well as attributes for each of these cars or each of these objects, such as, its location, its pose in the world, height, color, all these different things that actually instantiate a particular asset in the scene. So this is just an example of how one scene is just sampled from a very randomly defined distribution for the attributes. So the cars are kind of all over the place and they're not rotated properly. So basically what we want to do, we want to start by learning this particular distribution. So we're going to first assume that the structure of the, so let's say structure prior of the scene is good. So when we're sampling from this probabilistic grammar, we're going to get some sort of trees that indicate the correct structure of the scenes, but we want to learn the distribution of the attributes. So the distribution of how this, let's say, cars or people are oriented and positioned in the world. And we want to do this by as little annotation as possible. In particular, the goal here is, can we just use images? Can we just to completely avoid having an annotation? Obviously, having this kind of trees labeled for real images would be very hard, but we wanted to push it even further, like not even assume that we have bounding boxes around cars. So can we just look at real footage and be able to still learn these distributions? And we're gonna have this pretty, simple model to do this. And it has these 3 learning stages to it. Essentially, we're going to start by sampling scenes from probabilistic grammars, and we're going to keep the structure of these scenes constant through training. So we're going to trust that the structure is good. And the first thing we're going to do is encode this scene with a graph neural network, and we're going to be training this graph neural network to produce better attributes for each of these objects in the scene. And the first thing we're going to do, how we're going to train this graph neural network, or GCN, is to make it repredict its original attributes. So initially, when we're sampling from this initial probabilistic grammar, we just have a prior for each of these attributes. So essentially, we're just training this GCN to reconstruct the prior. And that's our initialization for the GCN. In the next step, we're going to bring data in the loop, where we're going to be sampling batches of real data, and we're going to be using this GCN to first sample the scenes. We're going to repredict the attributes, render these scenes, and we're going to use some distribution matching to train this GCN. So essentially what we want to do is have a batch of real data, a batch of render data, and make them look similar in distribution. And we're going to use MMD here to measure the distribution similarity. And all these gradients go back to the GCN. And obviously here, the renderer was not differentiable. At the time, there was no Mitsuba2 or whatever. So here, we're just using numerical gradients. So you're just perturbing each parameter at a time and computing the gradient. Note that the way we define this requires, again, no label for each of the objects. We're just doing this by extracting features on both of the images and computing the metric. Then if optionally we have a little bit of labeled data or labeled real data, we can even optimize this data, this generative model, such that if you train on this generated data, some black box task network, and evaluate it on real data, its performance should be optimized. So it's kind of like meta learning, where now you want to optimize your data such that it's going to produce best rate network on the held out test real data in this case. And this is non-differentiable. So here we're just training this with RL. So a couple of results. On the right side is just random samples from the Kitty data set. On the right side is the samples from this initial probabilistic grammar, where the structure is supposed to be good, but the attributes are, random, uniform, whatever. And in the middle are scenes that are optimized with MetaSim. So basically, the attributes have been transformed to match more closely the real data. So you can see that MetaSim really learns how to align cars here with the lanes, and brings pedestrians closer to the camera the way they are actually in Kitty. And so on. So it's a pretty nice result. So this is going to show what's happening during training. So remember, the first frame is going to be the sample from the initial probabilistic grammar. Every next frame is a snapshot of what MetaSim is trying to do with this scene during training. So it's basically learning how to move these cars around to better match the target data. And here is another example. So it very quickly figures out that the cars should be aligned with the road, which is kind of neat. And of course, this is a generative model, so you can create any number of scenes as you want. Cool. So one question, of course, is how can I evaluate now the value of the generative model that I train? And one possible answer is, well, let's just sample from this model and use it to create like a little computer vision data set. So we're going to be sampling a bunch of images. We're going to render its corresponding labels. In this case, we're going to train an object detector on this data. And then we take whatever object detector is out there, train on now this labeled synthetic data set, and evaluate performance on a real data set. And this is basically reported in the table. So in this particular case, we're evaluating the initial probabilistic grammar, so scene sample from that. And then when you optimize these scenes, you get improved performance, actually quite a bit. All right, so far we have basically assumed that the grammar that someone has written a pretty good structural prior, and we only learned the distribution for the attributes. But what if we want to have artists, not even do that, kind of just write the rules, and we want to basically learn the structure as well by looking at data.
Sanja, sorry to interrupt again, but it sounds like you have some Slack notifications, and we can hear those.
Oh, yeah, sorry. Let's hope that they stop.
Okay.
All right, so here we want to learn structure as well, and we're going to be using probabilistic context-free grammars. So essentially what we want to learn is a generative model of strings that are constrained by the grammar, okay? So on the left side, we have some example grammar with the rules, and context-free grammar essentially has terminal and non-terminal symbols, and it has rules. And these rules are essentially telling how to expand a symbol into a new set of symbols. And you stop sampling when you only have terminal symbols left, okay? And basically, now we want to introduce learning here. In probabilistic scene grammars, in fact, you have probabilities associated with the sampling rules, and we want to learn here those probabilities. Okay, so essentially what we're going to do is we're going to sample a latent vector, and we're going to use an RNN, which at each step is going to sample a rule. So we're going to convert this latent vector into some unnormalized logits of the rules. We're going to use masking to basically figure out which rules are valid for this particular symbol. We're going to sample a rule, feed that back into an RNN, and sample until we hit terminal rules. Right, so essentially each sample from this RNN represents this string. This string is essentially a scene graph, and then we sample the parameters, and then we can render this particular scene. So it's a little bit more complicated than the original metascene, which now learns structure, and metascene is kind of in the inner loop, which learns the parameters. So one thing that we noticed, the first thing was obviously we want to use MMD to train this, but it actually turns out to be very hard, because if you look at this, it actually requires making discrete choices, right? Because I have a discrete sampling rules here, and I have a non-differentiable rendering in the loop. So we need to use RL, and MMD just wasn't working. And the reason is that, how we computed MMD before is you have a batch of real data, a batch of sample data, and you compute the score. So you get one score for an entire batch of sampled scenes. And credit assignment in that kind of setting, we just wasn't training any successful models. So essentially what Amlan did here is he has a way of computing the likelihood of each individual sample scene under all synthetic scenes, compute the likelihood of a scene under all real scenes, and then we're going to use as a reward in our RL just the likelihood ratio between these two likelihoods. Okay, and we use a couple of approximations here. So to compute the likelihood, we're just going to compute it non-parametrically by fitting KD to some features of the scenes. Okay, and again, we're not going to fit KD to the entire or like a large set. We're just going to use a batch to compute this. Okay, and one essential thing is the same as in the original metascene was it's essential to actually pre-train this model on just the prior. So just being able to reconstruct the prior. That was the initialization. Okay, a couple of results. So on the right side, again, samples from Kitty. On the left side, samples from the probabilistic grammar, where now the structure is really badly initialized. So you can see there's almost no cars, there's no pedestrians. So the scenes are almost empty. And in the middle now is this metascene 2 that now learns structure and parameters. So you can see that it's placing a lot more buildings, and placing a lot more cars, pedestrians. And I'm actually very surprised how well it actually does this, given that it doesn't use any supervision. This is just kind of showing how well it's able to reconstruct the target in this kitty. And what we're showing here is a histogram of the number of cars in a scene. So in the dark green is basically real kitty scenes. Again, 0 would be no cars, 5 would be 5 cars in a scene. And the prior is in orange. You can see that it's very badly skewed toward very few cars. And then the light green, the lime, is the learned So the histogram after learning. So you can see that it's almost perfectly matching the histogram of the cars, which I thought was quite amazing, given that there's no supervision. And again, we evaluate this trained generative model by, again, training a network on this synthesized data and evaluating on the real data. And we see that it improves over not training the structure as well. Okay, cool. So, this was a model that we employed for driving, but, with all the pandemic and stuff, I was quite inspired to try to simulate human body as well. And we've done just like baby steps in this direction. I think a lot more is gonna come. So here we're gonna try to synthesize cardiac CTs. Okay, CT volumes is essentially a scan around the heart of the human body. And again, we want to do something similar as in the previous project, only now we want to create a CT that looks realistic with a corresponding label, such that someone can now take this data and train some segmentation model. And I felt this was very important for medical imaging because there is particularly annoying to annotate data because you need doctors to actually do that. So again, we're going to have a generative model here. So we have, some latent vector. From this latent vector, we're going to be mapping. So we're going to be predicting a mesh. In this case, we just use PCA to parameterize all the possible variation of a heart in this case. And we're only predicting the PCA parameters, so low-dimensional parameters of this model. And we also synthesize material map, which is essentially saying, the material each place in this particular volume, like a very low resolution material map. And then we do that in some sort of a canonical space. And now a hospital comes in, right? We want to actually simulate data for a particular hospital. And each hospital turns out to have very different CT scanners. So it was, either the choice was we want to learn this model for each particular hospital, but the goal here was, can we actually train a model that can serve all different hospitals? And so here we kind of have this world model of how hearts and its material looks like. And then we're using device parameters. Some, I don't even know how CT scanners work, but something that can physically simulate, if I take this 3D mesh and material, what's my CT scan actually going to look like? So this creates a pretty neat looking CT scan. And then we have like a local hospital dependent conditional GAN that essentially impaints it better, right? Because if you notice here, we can only model the heart. So we're not modeling the surrounding organs. So we're hoping that the conditional GAN that's going to be conditioned on this mask and the material can actually impaint other parts of the CT volume as well. And that essentially can now render any number of volumes along with the segmentation labels, which is essentially just here in the mask. And here we're just using GLOW to train this. Essentially, GLOW, I think, is generative latent optimization, jointly optimizes both the latent vector and the generative parameters and just uses reconstruction losses. And yeah, this turns out to be working pretty well. But what I really like about this model is that it can operate in some sort of a federated fashion. So you can imagine having a central server that is only training like shape, so knowledge about the shape of the heart, knowledge about the material, irrespective of any hospital parameters. And then on each individual hospital, you can fine tune the conditional GAN, you can use their device parameters, and only send back again the gradients with respect to shape and material. So everything is differential private, and you can also leverage all the other hospitals' data in order to simulate the data on your own site. So these are some examples of this synthesized data. So these are just like two different examples, left and right. The first two columns is our synthesized CT volumes with masks, and on the right in each column is closest or nearest neighbors from the real data, just to showing that we're not completely memorizing. It's actually, inventing new things. And again, how are we going to evaluate this particular generator? We're going to do something similar as we did before. So we're synthesizing a bunch of data, label data, we're training a segmentation model and then testing it on some held out real data. So here, different label sizes means how much label data I actually have on the hospital side. And we're only using that to train the conditional GAN. And here is just ablation of different versions of our model, but essentially lower bound is if I only use a little bit of hospital data, in this case, only 4 labeled volumes, what's the performance I get on the held out data. Upper bound is if I actually have relatively a lot more label data on the hospital side, so I spend a lot more money to actually label that data. So we treat that as upper bound. And then hours here would mean if I use a little bit of real label data, but a lot of synthesized data to train this. So you can see that the performance kind of nicely improves over having only real data. And sometimes it even outperforms having more data, more real label data. And the reason is just because we can synthesize, an infinite amount of data here. And we also had some ablation with respect to federated learning. I'm not going to go into here. This is just a fun demo we try to do where someone can now play with this heart because it's just PCA, so they can play and control the 3D shape. And now you can click generate slices. You can select any cardiac shape and you can synthesize the volume and you can browse through the volume. So you have kind of like, interactive generation of data. And of course, the mesh represents the label for this particular volume. Cool. And then, that's going, what we're going there is, generate the full human body. That would be a dream, right? Not just the one shape, but actually a lot more. Okay, cool. So that was kind of like generating scenes. And we've done a little bit work on also how can we go from pictures into 3D assets. So how can we assist artists in creating actually the 3D models? Can they just take a bunch of pictures and get really good, at least good initialization to create their models? So, I think by now it's a very established way of how can you do this without needing to have 3D supervision. And we know from graphics that images are formed basically as an interaction of geometry with light. And here what we're gonna do is gonna try to train a neural network that goes from an image into a mesh, light, and texture. And then this is gonna be fed through a renderer that synthesizes an image or renders an image. And the loss is only going to be operating on the image. So the rendered image, the predicted, basically rendered image with the input image, and try to minimize that loss. And of course, if the renderer is differentiable, then you can backprop through this entire, rendering pipeline and train this neural net. There's a lot of bells and whistles into making this work. You need, a mask class. You need to know that, you need to have multi-view data, at least in training, or these results are actually not going to work. This is, I'm not even sure I should go into the details, but this was our own differentiable renderer, which basically is just rasterization based. What does that mean? I have, some 3D mesh with some parameters on each of the vertices, which is, for example, just color. You're projecting that into the image, and how you now compute the color for each of the pixels is basically just, barycentric interpolation of the colors on each of the vertices. That would be like a simplest way how you can do that. And of course, you can have different lighting models that make that a little bit more complicated. But, this entire pipeline seems differentiable, right? Because now the color of each pixel is just, a differentiable function of these colors on the 3D mesh, and I can backprop through both the vertex position and the colors. And one thing that, one needs to be careful is that in the original formulation, you can only get gradients for the pixels inside each of the projected triangles, but you also want to have maybe a little bit of loss outside. And here we're just using kind of like a, probability of a pixel belonging to each of the faces, which kind of fades off with the distance to the closest triangle.
Sanja, you've got about 5 minutes left.
All right, yeah, I think I can do it. So these were our results on just synthetic data. So input image, 3D mesh out, texture, whatever, it kind of looked good. These are results on real images and birds. it also looked good. What no one is telling you is that all these methods are using quite a bit of supervision here. So again, camera information, key point information in this case, and masks. And we tried it also on Pascal data set, which also has a little bit of supervision, but a lot less data. And you can see the results were pretty bad in my opinion. So the middle would be predicted 3D mesh and texture and re-rendered in the same view. And on the right side was a baseline. So the baseline was really doing not great, but we were also not doing too good. And this was a little bit concerning. So we wanted to maybe make this a little bit better. And one problem that I thought made these results pretty bad is because there was a lack of data. There was only like 3,000 different cars, and there were so different orientations. And the question was, how can we get better data to train this model? And we had a pretty simple solution to this. We all know that StyleGAN is generating really good looking samples, right, for faces and even for cars. So these examples over here are actually samples generated by StyleGAN. It looks very realistic, right? And one of the person in the lab was trying to play with this StyleGAN code, and he found that there is like this viewpoint code in StyleGAN, where if you keep the rest of the code, which we're gonna call the content code, frozen, but you're only playing with the viewpoint code, then you get basically the same car rendered in different viewpoints, which is pretty much the data you need to train, all those differentiable rendering pipelines, a lot better. And if turns out that if you keep the viewpoint code fixed, so here different columns would be different selected viewpoints, and vary the content code, essentially for each viewpoint, you're getting different cars rendered, almost matching that same viewpoint, which is basically nice, because now we have control over viewpoints, and for each viewpoint we can render through StyleGAN, infinite amount of different examples. And that's exactly the data we need. We didn't change almost anything except for the fact that we changed the differentiable renderer to deal with a little bit of noisy camera, just because these viewpoints are not perfectly matching across different cars. So we're optimizing the camera as well during training, and we get results like this. So I think there's a stark contrast difference with the ones we got before on Pascal. Again, this is predicting a 3D mesh and generating in the same, rendering the same viewpoint, and this is just showing that the 3D is actually working pretty well. So these are other viewpoints. This is comparing basically, the quality of this trained network if you use this hours, which is StyleGAN data, or the Pascal data, which is, a small real data set. So you can see there's a really stark difference between the quality of these predictions. So the previous one was tested on Pascal data set, so you can say that it's in domain. If you just take a bunch of pictures from the web and you test the Pascal model with the StyleGAN model, you can see that there's just a huge difference. The Pascal model completely fails. And of course, this model works with any images. So now you can create, as many 3D assets as you want. So I just wanted to kind of show this little demo, and then I can stop. Where now we have like a 3D scene, and the artist now just takes a picture and gets the 3D model up. And this is real time, so we're not pre-computing these 3D models here. So it's as fast as you see. I'm not sure whether you noticed, but these cars actually have material associated with it. And this is because we're now able to predict part segmentation as well. So we can say that something is a windshield, something is a light. And we can do this to a very fine-grained level. And then you could just replace the materials of the car with appropriate materials like emissive lights or transparent windshield. I'm not sure. Do I have time, or I finish here? Adam?
You can have a couple more slides maybe, but we're...
All right, I'll take them. I just wanted to show what you can do on top of this. So you can look at the pipeline so far like this. So you have a latent code, which is StyleGAN. And we're using style again to generate multi-view data, and we use this multi-view data to learn this inverse graphics network, which can now take a picture and predict, mesh, light, texture, whatever. But can we go a little bit further, and can we make StyleGAN actually be a real, neural renderer? Can we make StyleGAN take as input mesh, light, and texture, just as a graphics renderer would do, and then make it synthesize an image? Okay, so we're basically just gonna close the loop in this particular pipeline over here. So from latent code, you produce an image. From that image, you can produce back mesh, light, and texture. And now we just wanna go back from some encoding of camera, mesh, texture, background back to the latent code. So we didn't do anything too fancy here. The only maybe thing that we wanted to do is have some disentangling. So essentially, we want to make sure that mesh, texture, and background each explain one particular dimension of the latent code, such that the StyleGAN code is going to be disentangled. And we train this entire network again, so end-to-end. Right, so the mapping as well as this inverse graphics network is essentially disentangling StyleGAN to be a graphics renderer. So input, so these are just input images. Here we're using this inverse graphics network to predict a mesh, a texture, and now this is a re-rendering of that prediction. And now we're feeding that prediction, mesh, texture, and the background of this scene into StyleGAN, or StyleGAN renderer, because now it has this mapping, and we can now render with StyleGAN, with this neural renderer. So essentially you get a dual renderer, which is one is graphics based and one is just again, which is, I thought, kind of cool. And you can do some cool tricks here. So in the first column is just a bunch of sampled cars, and now you can do some swapping between different things. So for each of these cars, we're just gonna run the inverse graphics network to get mesh, texture, or whatever, and then we're gonna be swapping different things out. So in the first column, we're swapping all the cars in the first column with the shape of the first car here in the red car. So the shape across the full column should be roughly matching the top left car. In the texture swap, we're swapping all the cars with the texture of the second car. So it's kind of working. In the last column, we're swapping background for the third car over here. So if you look at this, StyleGAN is still not perfectly disentangled, but it's kind of doing a reasonable job, and it's a reasonable dual renderer. And yeah, I think I'll just stop here. So if you guys have any questions.
Thanks, Sanja, for the great talk. It was really nice to see the ability to generate everything from sort of objects to scenes. So for the audience members, if you have any questions, you can sort of raise your hand and we'll unmute you to ask that. And in the meantime, actually, I did have a question. So in the earlier part of the talk, you showed that we were generating scenes, and there were these essentially category-based or semantics-based relationships that were being used. And I just wanted to hear your thoughts on if we need to go finer in that. For example, I often see bikes being hung behind cars, but typically not behind sports cars. And if that's something we really need to capture, it's sort of good for now.
I think I would love to capture that, right? And right now our like procedural grammar is super simple and it's context free. So we cannot actually handle a lot of these different more complex dependencies. But I would love to, as a future step, to scale it to have, first of all, support a lot more objects and also not be context free, right? So capture maybe more complicated scenarios, right? Next to a sports car, I can only have this and this, and the road needs to look nicer because sports cars don't go into not nice roads, right? So I feel like that's where these models can be even like really shine, because that's the models that artists would have a lot of trouble tuning because there's just so many different parameters. But I think that is a little bit far away, particularly maybe without any supervision.
Okay, so, thanks. And I think we have one question from Kostas. Kostas, you should be able to speak if you unmute. Sorry. I'm not sure if, I think he raised his hand, and if you try to unmute, you'll be able to speak. Or,
he changed his mind.
Okay, I think we might just move on in that case. Thank you again for the great talk.
Yeah, thank you for inviting me.